Hello physicists, we are going to start lesson 5.3, which is on Kirchhoff's laws. Our lesson objectives are going to be focusing on series and parallel circuits and looking at how Kirchhoff's laws apply to series and parallel circuits. Before we go on, I just want to say that we are going to, from this point on, I know we've been talking about our circuits in terms of the actual flow of electrons from negative to positive. So we've been talking about the way these are actually flowing, but from now on, we are going to switch around to looking at the conventional current flow here. And the reason that we're going to use conventional current flow is actually, there's a couple of reasons. The first is that this is what the vast majority of textbooks and university courses are going to use, and so we might as well get used to using conventional current flow. And second is that it's actually easier to consider a collection of positive charges rather than negative charges, because we remove that pesky negative sign in our calculations, but we can also acknowledge that the amount of charge is equivalent. So if we had well, let's just think of it in terms of the fundamental charge. So the fundamental charge of one electron is going to be 1.67 times 10 to the negative 19 coulombs. And if we're thinking of it in terms of a positive charge, then, oh, sorry, this would be negative, right? And so if we're thinking of it in terms of a positive charge, it's going to be equivalent, just opposite. So nothing's going to change. Our Ohm's law is still good. Everything is fine. We're just going to remove that negative sign from our calculations. Okay? So again, we are, at this point, we're going to switch from the actual electron flow to conventional current flow. And remember, we said that conventional current flow, where we're thinking of it in terms of positive charges moving from the positive to the negative terminal. Okay, so let's go down, and we're just going to clear up a little bit of jargon first, so circuit jargon. And actually, before we even get into talking about series and parallel, maybe we'll just go back up here really quickly, and we will talk about a little bit of extra information here. So first of all, let's talk about circuit components. So here we're talking about things like voltage sources, such as batteries, ones we're most familiar with, and resistors. And again, a resistor is anything that's going to decrease the flow of charge. Okay, so we could be talking about light bulbs here, we could be talking about actual resistors. Okay, and it's just important for us to have some idea of circuit components, because when we go to talk about things like junctions, and a junction is also called a node. These are, well, one junction or node is a connection. Between two components. And a branch is just going to equal something that connects nodes. So it's going to connect two nodes, and this will be the same as the number of components. So let's just draw a quick circuit and see what we're talking about here. Put a resistor there, put a resistor there, and we'll come here and put another resistor here. So a junction is going to be a connection between any two components. Our voltage source here, this is one component. Then we have a resistor, that's another component, a resistor, and a resistor. These are all components. So a junction is going to be a connection between any two components. So here we have a junction, a connection between these two components. Here we have a junction, so this is going to be, let's call it a node 1. Here we have node 2. It's going to be a junction between these two components and these two components. Sorry, between these two components and these two components. And then we're going to have another junction here between these components and our voltage source again. So we've got 3 nodes. And we can talk about branches too, and we said this is going to be the same as the number of components, and it's going to connect nodes. So we have this resistor here, this is branch 1 connecting these 2 nodes. Branch 2 here is going to be, well, let's look at it. So we've got these 2 nodes, node 1, node 2 are being connected by branch 1. Node 2 and node 3 are connected by branch 2, branch 3. And node 3 and node 1 are connected by branch 4. So we've got 1, 2, 3, 4 components, and we've got 4 branches. Okay, that's just going to help when we're looking at circuits later and talking about these different components and how to identify a node or a branch. Okay, so now let's go down here and we'll talk about our series and parallel circuits. So a series circuit is one in which the flow of current can take only one path. It means there can only be one loop. So again, if we look at our battery here, actually let's highlight this. This is an important definition for us. Okay, so we've got positive and our negative sides here. We said we're going to follow conventional current, so we're going this way. And you can see that there's only one path, there's only one route for these, for the charge to go, or the current to go. Okay, and if we've got light bulbs, this is just so this is a pictorial diagram showing actual light bulbs here. And so these are equivalent to these in a schematic diagram. So these represent light bulbs. Okay, but big takeaway here, a series circuit is one in which the flow of the current can only take one path. Okay, a parallel circuit, on the other hand, is one in which the flow of the current can take 2 or more paths, or there are 2 or more loops is another way to say that. So we can see that we can go from here, we can come this way. Okay, but we could also, some of our current could go this way, and we could also go this way. Okay, so we've got multiple paths that we could take here. And again, in our schematic, we've got our light bulbs here, and we can see, again, following on our schematic, that we've got multiple paths here. Okay, Now we're going to move into, now that we understand the difference between a series and a parallel circuit, we can now apply those ideas or apply Kirchhoff's law to parallel and series circuits. So Kirchhoff's laws are applications of the law of conservation of charge and conservation of energy. We're very familiar with the idea of the conservation of energy, but let's make a quick note here about conservation of charge. So conservation of charge just says that charge going into a node must be the same as the charge leaving the node. Okay, so we're going to look first at Kirchhoff's current law. This is called the junction rule. So the current law is how we'll most likely refer to it here as. And what it's saying is the sum of the current flowing out of a junction will equal the current flowing into a junction. And if we think about what we've learned before, so now we're going in this direction. So we're starting off, we can call this I naught, or we could call this the total. This is the total amount of current that we're going to have. And as we go through, we know our current is really made up of these charges, and now we're thinking of them as positive charges. And so we're not creating more of these. We can't lose them in a closed circuit. So if some of them go this way and some of them go this way, well, the total of the ones that go this way, so we're going to get I1, remember this is I total, we're going to have I1 and I2, and so I1 plus I2 must be equal, so I1 plus I2 must be equal to the total number that we had at the beginning. So we can represent that actually numerically here. We say we've got 7.5 amps, and perhaps we've got different sized resistors there, so we're going to have 5 amps going through this branch, and we're going to have 2.5 amps going through this branch. Okay, but if we add them up, so this is our I total has to be equal to our I1 plus our I2. Okay, so this is where we've got more than one path. So this idea of the conservation of charge is where we've got more than one path. However, if we've got a series circuit, so let's draw the same sort of thing, only now we're going in series. Well, now our charge coming here has got nowhere to go. So even though we know that we are going to lose some potential energy here, and our current is going to slow down, we're still going to have the same number of charges going here. Again, we can't create these things, we can't lose them, so the number before has to equal the number afterwards. So in this case, and we could even add another resistor here, and then we say, well, again, we can't change, so I3 has to be the same as well. So in this case, we would get I total must be equal to I1, which must be equal to I2. Okay, so these are our current laws for parallel and for series. And if you need to go back and rewatch that part, just make sure you understand Why in parallel? When we have a junction or a node, our total current is going to equal the sum of our currents, whereas when we have series, our total current is going to equal our current at any other point. Okay, so just keep that in mind. Okay, so this junction rule is conservation current law. This is, and I think I made a note already, yep. Junction rule, conservation of charge. Okay, so Kirchhoff's voltage law, or the loop rule next. Here, let's make a note right off the bat. This is going to be conservation of energy. All right, and we know if we're talking about voltage, we're talking about the potential difference, we're talking about the joules per coulomb, right? And we're talking about losing our energy. So the drop in voltage is really a loss in that potential energy. So it makes sense that when we're talking about the voltage law, we're talking about conservation of energy. Okay, so in this one, for Kirchhoff's voltage law, the sum of the voltage increase equals the sum of the voltage decrease in a loop. So what this means is if we've got 10 volts here, let's say, okay, so we've got 10 volts of energy. So each of, remember this is joules per coulomb, right? Volts is the same as joules per coulomb. So we could say that we've got 10 joules of energy for each coulomb charge we've got here. And now, if we've got a parallel circuit, so we've got multiple paths here, well, let's think about what happens if we go across this resistor. So if we have these coulombs, because we're thinking of these in terms of joules per coulomb, or we could think of it if our charges go this way, well, we have to, for us to come back to this path, we have to have lost all of our energy across. So we have to have lost all 10 joules across this resistor because we're going to come back this way and the cell is going to recharge us. So we're going to get that 10 volts back, right? We talked about the battery is going to maintain a consistent voltage. So if we come across this path, we're going to have to lose our 10 volts per coulomb, or 10 volt, sorry. We're going to have to lose our 10 volts, or we're going to have to lose our 10 joules per charge so that we end up with 0 volts here, and our battery will come back and give us those 10 volts back. Same thing here for the ones that go this way. So some of them are going to go this way, and they're going to lose 10 joules per charge. Some of them are going to go this way, and these ones are also going to have 10 joules per charge. Again, what's going to happen here? Well, we're going to come back. Again, we're going to have to lose all 10 joules per coulomb so that we can come back to the battery and regain it. Same story here. We're going to have to lose our 10 joules per coulomb, or our 10 volts, so that we can go back and our battery can again restore the 10 joules per coulomb. So in this case, our V naught, or our V total, is going to equal our V1. So our V1 at this point, V2 at this point, or V3 at this point, all have to be the same, because across that resistor, due to conservation of energy, what we pick up here, we have to lose at each of these. Okay, so that leaves us with the equation for a parallel circuit. We have the total voltage equals our voltage 1 equals our voltage 2, and so on. Okay, now in a series circuit, if we had the same thing where we've got our charges, with 10 joules per coulomb. Okay, well now if we lost all of that energy right away across this resistor, if we lost all of that across this resistor and we ended up with 0 volts here, well, we'd have a problem because then we'd get to this resistor. We know we're going to slow down and lose potential energy, but we've got nothing left to give. So in this case, in our series circuit, when we're in series, we are going to lose a portion. So this is going to be our V1, this is going to be our V2, this is going to be our V3. We're going to lose a portion of our total voltage across each of these resistors, which means that our voltage total is going to equal our voltage lost across the first element, okay, plus our voltage lost across the second element, plus our voltage lost across the third element, and so on. Okay, so now and these have been shifted, but here's our parallel voltage law, here's our series voltage law. And again, note, the junction rule or the current rule is based on the conservation of charge. The loop rule or the voltage rule is based on the conservation of energy. Okay, now if we want to figure out the resistance of resistors in series, or if we want to figure out the total resistance of resistors in a circuit, like in this diagram below here, we can use the information that we've just been given, and along with Ohm's law, we can figure out the total resistance in this circuit. So okay, we're in series here, so we go up and we take our voltage law in series, states that, again, conservation of energy for our voltage law states that in a series circuit, our voltage total is equal to our voltage 1 plus our voltage 2 plus our voltage 3. Our current law in series, okay, and this is again conservation of charge, is saying that when we're in series, our total current must equal our first current must equal our second current, so our current has to be the same at every single element in our circuit there. So now we can come through and we can substitute in our Ohm's law here into our voltage law equation. So let's make this clear. We've got our voltage law equation. And we'll use it for this. So we've got 3 resistors. So we're going to have 3 different voltage drops here. Okay, and now we're going to substitute in Ohm's law into the voltage equation. So our V's are going to become IRs here. So we're going to have our V's become IRs. So our I total plus our R total is equal to I1 R1 plus I2 R2 plus I3 R3. Now we can say, well, what do we know? If we come back up here, what do we know about our current when we're in series like this? Well, we know that all of these things, all of these individual currents have to equal our total current. That gives us something really handy that we can do. We can factor these out. These are all equal to IT. So we can factor these things out. We can call them all IT. And that leaves us with R1 plus R2 plus R3. We can cancel out our IT on each side, and it leaves us with this equation. So in the general case, we get our total resistance equals our R1 plus our R2 plus our R3. Okay, and this is when we are in series. Okay, so if we want to figure out the resistance, the total resistance in series, this is our equation we're going to use. And this is just a little bit of common sense stuff. When resistors are added in series, the total resistance is always greater than the largest resistor. We could draw this really quickly. So if we've got a 10 ohm resistor and then we add another one in series, well, it's common sense. When resistors are added in series, the total resistance here, which we figure out through this equation, is going to have to be greater than the largest resistor. Well, obviously that has to be the case. We're adding our resistors, right? So this was our R1, we're adding our R2. So yes, this is common sense. And it gives you a check. So if at the end of your question, you've got a single resistor that's larger than your total resistance and you're dealing with a series circuit, you know something's wrong. Okay, so that provides you with a little check. Okay, let's go to resistors in parallel. So if we want to figure out our total resistance for resistors in parallel, we are going to go back and, well, we're missing it here, so I'll just draw it in. We're going to talk about our current law, and we're going to be talking about in parallel. So our current law when we're in parallel is our I total is equal to our current 1 plus our current 2, and in this case we're going to have 3 currents. Here's our current coming in. Okay, and the voltage law in parallel tells us that our voltage total is going to equal our voltage 1 plus equal to our voltage 2, which is equal to our voltage 3. So we're going to do the exact same thing that we did before. We are going to substitute in Ohm's law into the current equation. Okay, except for this time, our current equation, so we're using this variation. Okay, so we've got the V over R, so we've got V total over R total, and we've got V1 over R1 plus V2 over R2 plus V3 over R3. Now again, what do we know? Well, we know that all of our voltages are going to equal our voltage total, and that allows us to factor out our voltage total. That means these all, let's rewrite this. This turns into voltage total over resistance total is equal to 1 over R1 plus 1 over R2 plus 1 over R3. We've factored out our voltage total. This is going to cancel out, and we're going to get this equation down here. Okay, and the way we're going to plug this in to your calculator, because this is going to be tricky, you're going to have to do some algebra after you figure this out, or you can use this notation here where you can just raise this part to the power of -1, and I'll let you figure out for yourself. I'll let you convince yourself that that actually works, because the -1 just takes us from, if we multiply both sides by power of -1, or we raise both sides to the power of -1, we get rid of the 1 over RT on that side. So this is how we're going to enter this in our calculators. And again, what you're doing is you're essentially breaking down this larger parallel circuit into this smaller circuit with one total resistance. Okay, now when resistors are added in parallel, the total resistance is always less than the smaller resistor. This is just by virtue of the fact that you've got 1 over your resistances. So if we again do the same thing that we did last time, Okay. And we now give ourselves multiple paths to take. Sorry, so if we're adding these things, we started off 10 was our smallest. Let's say we've got 20 ohms, 30 ohms. Well, we're going to have our resistance total is equal to 1 over 10 ohms plus 1 over 20 ohms plus 1 over 30 ohms. We're going to put those things all, it's going to end up being 1 over your answer for everything that's in the brackets here. And so because of that, when your resistors are added in parallel, your total resistance here is going to be less than your smallest resistor. And again, I'll let you do the calculation and convince yourself of that. Okay? Now, for where we're going to get to today, because we've already gone for quite a long time, we're not going to get into the questions just yet because the questions are going to depend on our ability to place what's called an ammeter and a voltmeter consistently in a circuit. We're going to need to know how to reliably place these things in a circuit to do some of the questions. So instead of getting you to jump straight into the questions, what I want you to do is I want you to do a little bit of research on these circuit devices. Okay, and I want you to figure out for these questions here, this smart task, I want you to mark the correct place where you will place an ammeter for the following circuit diagram. So this is your homework for today. Is to research where are you going to place an ammeter in the circuit and where are you going to place a voltmeter in the circuit and why are you going to place them where you place them. Okay, so in summary here, if we're talking about series circuits, we've got Kirchhoff's current law, and the current law we've got conservation of charge, and in a series circuit we've got our voltage law using our conservation of energy. And we saw how, from those two things, we can come up with a expression for our total resistance. For parallel circuits, again, we've got our current law, we've got our voltage law, and then we've got our total resistance expression that we've made up. Okay, so again, last little thing, let's just remind ourselves these are equivalent to the total. Okay, and then where we're going to head into next time is combination circuits. So we're going to have portions where we're looking at things that are in series and things that are in parallel all combined into one circuit, and we're going to reduce them down into something simpler. So we're going to go from a more complex circuit diagram like this to something that's a little bit more manageable like this. Okay, but actually we're going to save this. This is going to be after we do our practice questions, but we're not going to get into those practice questions until we know exactly where we're going to place our ammeters and our voltmeters. So I want you to know what these things are and where you're going to place them in the diagrams, and I'll see you next time.